Okay, so I'm going to actually follow up from Zach's presentation and tell you a bit about hierarchical reinforcement learning and how it supports generalization. And this is part of my work on structure learning, and I like to spend a little bit of time telling you what I mean about structure learning. I think it relates to the symposium in terms of building models of the world, and more specifically of how we interact with the world. So if you have those four computers here, one way you could try to find structure here is by grouping them by how they look. For example, the three are desktop computers, and this is a laptop. But what is probably more behaviorally relevant is to group them this way, because those three are Mac computers, and this one is a Linux computer. Okay, and so what matters here for this grouping is how you're going to interact with the computer rather than what the computer looks like. Okay, and how you're going to interact with the computer is something I'll call a rule, just to simplify it. You could call that a task set or a strategy. And what I try to understand is how we learn those rules, those hierarchical rules, and how we learn to create the state of rules over which we operate. So, for example, how many rules there should be in the state, and what is relevant for figuring out what rules to learn. Okay, so in this talk, I'll tell you first a bit about my previous work on hierarchical rule learning, and then I'll move on to try to show you that fairly simple computations can achieve hierarchical reinforcement learning, and that's the work of Maria, who gave a flash talk earlier and who has a poster. And in the third part, I'll try to make it into more interesting kinds of rules, so more complex kind of rules, and that's Jimmy's work, who also has a poster. Okay, so let me give you an example of why I think hierarchy is important. So imagine you're in this situation, you're working on a Linux computer on MATLAB for some reason, and MATLAB crashes, and you're going to have to select an answer, and your answer will be to type this magic formula here that will kill the MATLAB process. And now if you're trying to find your PowerPoint presentation, you're going to type another answer. So you're going to have another reaction to this state of the world. Now, if you're working on your Mac computer, instead, your answers are going to be fairly different. You're going to type this time a magic set of keys that will help you kill the process or find your presentation. Okay, so you could represent this, model your interaction with the world here as having four different states and four different actions. And what you have learned, or what you need to learn over time, is just to map those states to those actions. But what we do, rather, and what I'm trying to understand how we do, is structure this information in such a way that when we see this computer, we select a whole set of policies that are tied to this computer. So, for example, with this computer, we select the Linux set of rules, and the Linux set of rules now tells us what to do when MATLAB crashes or when PowerPoint. I'm looking for my PowerPoint. And then we also have a Mac OS set of rules that we select with in relevant contexts. Okay, so if you represent the environment this way, you still have four simple actions here, but now you are representing your states differently. You have those two states here of those two events. And then you can abstract away this low level and say that on top of that, you have more abstract states. So, for example, the context here of those two computers in which you select a set of rules. Okay, so that's where the hierarchy comes. You have abstract contexts that make you select make abstract choices like roles or task sets. TS here stands for task set. And then once you've selected task sets, you select an action response to a stimulus. Okay, so to test how people learn these kind of things, I do it in the lab with much simpler setups, so with colors and shapes as context and rules, and I try to see if people actually learn with this kind of hierarchical structures. Okay, so this is what the experiments look like. Participants, human adults, young adults, look at a colored shape on the screen, and then they make a choice, one of 4 actions. And at the beginning, that choice is random because they have to learn, so they don't know what to do. They get feedback. The feedback is deterministic and truthful and does not change over the course of the experiment. So, for example, if you get this correct feedback here, you know that you should pick the index finger for the book triangle. And then they go on to a next colored shape until they've learned very well. So something like 80 trials, 20 iterations of each of 4 different colored shapes. Okay, so how can we learn this? Well, you could learn this just by classic reinforcement learning, but I'm not going to show you that right now. I'm going to show you how the model I designed to capture this hierarchical idea. So the idea here is that we're going to learn stimulus associations, and for example, the shapes are going to be the stimuli here, and that's going to be one set of rules, one task set, that we select in response to a context. And we might have multiple contexts in which we have to select different sets of stimulus action association. And a key assumption of my model is going to be that instead of learning a set of associations for its context here, we're going to cluster the context together and assume that there are those latent, unobservable, or partially observable variables that are what is currently a valid set of rules. And that's what we're trying to infer, what the task set is. So we're clustering those contexts around task sets, and then condition on those task sets, we learn stimulus action associations. Okay, so that's more efficient. And then what the model does is figure out how to create this latent, this state of latent task sets. And one way to do that is to say, okay, well, what do I do when I encounter a new context, or a new computer, for example? We use a non-parametric Bayesian prior, Chinese virtual process prior, and that's, in this case, only means that the probability of associating this new context with another task set is going to follow a rule of popularity. So maybe if you get a new computer, you're going to be most likely to try out behaviors that have worked most often for you with other computers before, but you might also try the Linux set of rules, or you might have encountered a Microsoft machine or Windows machine and have to create a completely new set of rules. Okay, that's where non-parametric is important, because it allows you to create new rules. Okay, so this this model makes a prediction that if you've encountered many different Mac computers, for example, in your life, but a single Linux computer, when you get a new computer and you don't know what operating system it works on, you should be most likely to try this one. And what's important here is that it doesn't matter if this is your work computer and you spend 80 hours working on it versus a few hours here and there on those ones. What matters here is that there's more variety around what's clustered on this one. So the prediction holds even if the frequency does not favor MacOS. Okay, so to test that in this experiment that I was telling you about, we have participants first learn about those 3 contexts here, C0, C1, and C2. That correspond, two of them correspond to one set of rules, and C2 corresponds to another set of rules. And then we give participants new contexts in which they have to learn to behave again. And we test a prediction that they're going to be more likely to try task set 1 than task set 2. And we compare this to a new context in which they have to learn a completely new task set. Okay, so we observe transfer. Transfer here is that learning, the probability of being correct as a function of a number of trials, is better for a new context that corresponds to an old rule than a new rule. So this hierarchical structure allows us to generalize past knowledge in this new context here. And more so if the old context is popular than not popular. So it might look here like there's no transfer at all. In average, the performance is the same. But actually, if you look more carefully, you'll see that the first trial here is below chains. There's 4 actions, so chains is at 25%. And then the slope here is very steep. And so if you imagine that you are in a new context, you don't know what to do, you try task set 1 first, and you get negative feedback, truthful feedback, you would be below chains on the first trial, but then you would be able to rule out that C3 corresponds to task set 1 and move on to task set 2 and learn really fast. So this is actually also evidence of transfer, despite it not being obvious in the first degree statistics. We can see that simply by taking those very first trials for all participants and classifying the choices they make, not as a function of whether they're correct or not, but whether they correspond to what you should do in a macOS rule or in a Linux rule. And it's very, very strong in all participants that they pick the most popular one, even though that task set is as frequent as the other one. Okay, so it looks like we use something like clustering to put together behavioral context that require the same type of behavior. And that makes sense because, the sensory evidence we get is very, very high dimensional, but if we can group it together into a few sets of behaviors that work all the time, so for example, how to work in an office or how to give a talk in a conference room that you've never been in before, you can then immediately generalize instead of having to relearn in each new context. Okay, so our model uses just fairly quite approximate tracking of uncertainty, but it does have this ability to create, to infer the size of the latent state space. And so in that way, it provides also a high-level exploration strategy, because instead of exploring action by action, we explore strategy by strategy, which allows for generalization. Okay, this and many other experiments that I did show that we seem to learn by creating hierarchical rule structure, and that this allows transfer and faster exploration. It actually also comes at a cost, at a behavioral cost. So in the second part, we wanted to ask how the brain might be implementing something like this, and Bayesian inference over chains restaurant processes is complex and might not be happening in that form in the brain. So we wanted to see if there's maybe a simpler way to do that. Okay, so reinforcement learning offers us a way to learn to select actions in response to stimuli, and this is one of the simplest versions of reinforcement learning, where we just estimate the value of here just of a state, or of a state in an action by using temporal difference reward prediction errors. And when we have those value estimates, we can transform them into a policy via a softmax, for example. Okay, so that's a fairly simple algorithm, a fairly simple set of computations. And so what we propose is that we could take the same set of computations, try to track not only the value of a state in an action, but also value of a context in a task set, and use that as a policy to select task sets in response to context, and then enforce a hierarchy here so that those low-level stimulus action values would be dependent on the task set that's selected. Okay, so the idea is that if we have a learning algorithm that can take states, make choices, and then learn from rewards at one level, the state and action, maybe we can do exactly the same thing at a higher level of abstraction, so between context and rules, and create this hierarchical dependence here. So why is that a good idea? Well, because we know that we have a circuit in the brain that does something like reinforcement learning. It's fairly established that these cortico-basal ganglia loops that get input from dopamine, that something like a reward prediction error, are implementing something like simple reinforcement learning. We also know that those loops are multiplexed in the brain, that they start at various points in in cortex, including various points in prefrontal cortex. And prefrontal cortex is also known to represent things more and more abstractly the more anterior you get in lateral prefrontal cortex. Okay, so the idea is that if we have those rules starting in prefrontal cortex, those loops starting in prefrontal cortex, they might be doing the same computation of reinforcement learning, just operating over a different state space, an action space, and a more abstract one. So the space of context and rules. And then we also know that those loops are not completely segregated, but have some trickle down. So this could provide this hierarchical influence over lower level action selection. Okay, so I created a neural network model that has those two components: one level that selects task sets, and one level that selects actions. What's important is that the task sets have no meaning at the beginning. They're just blank pointers, and they can only come on taking meaning as they influence the selection of actions at the lower level. We trained this biologically plausible neural network with a single reward prediction error signal. And when we do that, we have a network that replicates what we see in participants, so that learns as fast as participants and produces this generalization, the positive transfer here in the experiment that I was showing earlier. Okay, so it's able to create those rules, this hierarchical structure, and use it for generalizing. With no Bayesian inference, with just reinforcement, very simple reinforcement learning computations. Okay, so that's a proof of concept that those simple computations in a network could lead to this kind of complex cognition that we're observing. So we wanted to test more specific predictions of this model, and that's where Maria comes in. She did a version of the previous experiment that's more playful, potentially targeted for developmental populations too. So the context, instead of being just colors, are seasons, and the stimuli are aliens, and the actions are those buttons. And there are 3 different task sets to be learned and 4 different stimuli. And the key new aspect of this experiment is that there's different amounts of points you can get for correct choices. And they're counterbalanced in such a way that the task sets are worth different amounts overall. And the key prediction of a double reinforcement learning model that we have is that you track 2 sets of reinforcement learning values just over different state and action spaces. So over context and task sets and over stimulus and actions. So by having those discrepancies here, we can test if we see in the behavior signs of both. Is this number here how long I've been, or? How long you have? Sorry? How long you have left? Okay, great. Thank you. Okay, so we can test whether participants' choices are sensitive to both both low-level value functions, so the value of a stimulus and action here, 7, for example, but also to the value of the context and task set here, 3.75. Okay, and first we need to check, of course, that participants do create task sets. So that's the slide that Maria showed earlier. I'm going to explain it just a little bit more. So the idea is that if you've learned this set of rules here to select the bed for the purple alien, for example, and now you're in a completely new context. You've never seen this cloudy season here. So you're choosing at random at first, and you choose the bed. The idea is that if you had learned this task set before, now you should know, the season now is actually the season in which I need to select this whole set of rules. And if you're able to do that, then next time you see, next trial, you see this alien, you'll know immediately what to do, what choice to make, before you've gotten any information specifically about this alien in this context, okay? And that's transfer, that's generalization, is you're going to transfer the whole set of rules rather than having to relearn in this new context. And so the predictions here is that even though you should be outchanged in the very first trial, you should not be outchanged in the subsequent trials, even though it's the first for those specific stimuli. Okay, so that's what we observe in humans. There's a positive slope between the first, second, third, and fourth trial. So participants transfer tacit knowledge, and this is our attempt to relate this to our hierarchical model. So as the previous speaker was saying, doing inference when there are latent states can be complicated, and in this task it's prohibitively complicated. We haven't found a way to do to fit the model to the participants' data. So instead we simulate the participants' data and see how well over many sets of parameters the model can match participants' behavior. And you see that only the hierarchical model can match participants' behavior here. Okay, so we see that participants learn structure. And now we can test whether the learning is sensitive to sets of values. So this is the learning curves at the beginning of each block as a function of the value of each item. And you see that they're very, very sensitive to this low-level set of values here. But they are also sensitive to the value of the task set itself. And that's controlling for the low-level value. Okay, so that supports our idea that participants are making choices at the high level using something like a reinforcement learning value. We can test it more specifically by looking at when participants make a choice for this alien that's worth 7 and then this alien here that's worth 7. The one thing that differs between them is that this one is in a context that's worth more than the other one. And so if participants are making choices at the high level that is dependent on the value, then they should be overall slightly better here than here. And that's what we observe, and that's what the model predicts. And again, the hierarchical model can capture human behavior, but the flat model can't. I'm going to skip this. You can go to Maria's poster for this. Okay, the take home here is that this kind of complex learning can actually be approximated in an implementation that's a multiplexing of fairly simple computations, just RL computations that we know have a realistic network in the brain supporting them. Okay, so in the last part of the talk, I'm going to make this again a bit more complex, and this is Jimmy's work, who also has a poster and will give a flash talk later. Because task sets are a bit boring, they're just very simple mappings, stimulus-action associations, and in our world, often we have strategies that are multi-steps. Okay, and one way people have been trying to look at this in reinforcement learning is with a framework of options. So just imagine this setup where your goal is to navigate in this environment and to learn to go to this goal. If you start here and just take very simple actions, just one spot to the next, it's going to take you lots and lots and lots of time to explore everything, and that's what's called the curse of dimensionality. Now, if you build an option, if you build a strategy, if you know a strategy already that will take you to this door here between the rooms, you can just jump to the door and then maybe jump to the other door and then just explore here. Okay, and if you are able to, if you have these kind of useful strategies and if you're able to use them well, you're going to be able to explore the space much faster and to learn much more efficiently. Okay, that's what simulations show here. What they don't show in this specific graph is that if you have bad options, instead it's going to make your life much, much worse. So if you had an option that took you to the corners, that wouldn't happen, for example. Okay, so the link to the previous part of my talk is that before I was talking about levels of abstraction. So we have the same RL algorithm that learn to select rules in response to context and actions in response to stimuli. And really, those rules or task sets are just one-step policies. Well, options are temporally extended policies. They say, okay, until you've reached the door, just take those steps, okay, to a first approximation. Okay, so I think the exact same setup that I was talking about in task sets might apply to options, and so we could apply the same type of modeling to it, and we could also test the same type of predictions, where the options will also, whether we also use options in such a way that allows for generalization and transfer of knowledge. Okay, so these are the questions we wanted to ask. And what's important about options is that an option can select a sub-option. So we also wanted to test multiple levels of hierarchy. Okay, so let me make it a bit more, so this experiment is tricky, so I'll make it a bit more concrete. So you might learn to make coffee, and making coffee involves multiple steps, for example, grinding beans and boiling water, etc. Okay, so I'm going to think of this as an option at a fairly low level. It's a low level of description of choices, and this is a slightly higher level of description. Making coffee might be part of making breakfast, and making breakfast, it might be this higher level option that you have that includes also making toast, which includes cutting bread, spreading butter, etc. Okay, so now when you're going to try to make lunch, you might again want to make toast to go with your soup. And so you might be able to generalize part of what you've learned before, but you might not want to generalize so much that you start making coffee again when you're trying to make soup instead. Okay, and then when you learn to make tea, you'll still want to reuse your skills you've learned previously about boiling water, but without grinding the beans. Okay, so the idea here is that with options, we can represent strategies at multiple levels of abstraction, and if we're doing this well, it might allow us to generalize precisely parts of the behavior that are relevant and not other parts. So this is what we're testing in this behavior. The way the experiment goes is that participants first see a shape, a circle, and as long as they pick wrong, they keep seeing the same shape. And then they see another shape, and as long as they keep wrong, they get no reward and keep seeing the same shape until they pick right and they get reward. Okay, no reward at this stage, and this is a single trial. So the idea is that you have to learn from this end of the trial feedback what the policy is. Okay, so this is one type of policies you might have to learn. Something that's important is that after you've selected the correct choice, you can't predict what the next action is. So you're not learning sequences of actions. You have to actually pay attention to the second stimulus. And also that there are two possible first choices and two possible second level images. And the correct answer for those second images is dependent on the first stage. Okay, so you can't just learn what the correct choice for the triangle is because it's dependent on whether you saw a circle or a square before. So this is where the idea of an option comes, because you need to select your whole strategy at this point and know what you're going to select here. Okay, so this is going to be our low-level options. And just to make it more easy to understand, this might be your coffee making, this might be your toast making, and this overall might be making breakfast. And this is what you'll learn in a single block of this task over 60 trials. And that's going to be blocks 1, 3, 5. And in blocks 2, 4, 6, you're going to learn different skills, like making lunch instead of making breakfast. Okay, so the idea here is that we can test whether participants create all those sets of actions and reactivate them, because if they learn in block 1, then something different in block 2, and then they go back to the same set of correct of policies in block 3, we can test whether they have savings from before and generalize what they knew before. And then we design specific testing blocks after that allow us to test transfer of those low-level options here, so boiling water, for example, but negative transfer here, because if you have the correct action 1 here, you expect the second one to be 2 and not 4. And another block that tests transfer at another level. Okay, so when we did that, we first look at the first level of choices, and look at how many trials it takes participants to get the correct action. Not how many trials, how many attempts in a given trial. We predict here negative transfer and here positive transfer based on those options. So that's what you see here. Up is worse because they have to try more choices before they get it right. So we do get negative transfer here and positive transfer here. We can specify that the errors they make here are specifically due to making the wrong type of errors, right? So here, if you learn to select action 1 for the circle, you might be making the reference that you should select action 2 for this, and that's the type of errors that they make here. Okay, and then in the second stage, we can test whether they have positive transfer of low-level actions, even in the context where they can't transfer the whole options, and negative transfer here. Those are completely new low-level options. And that's what we observe again. No difference here, which is positive transfer, and slower learning in block 8, which means negative transfer. Okay, so Jimmy generalized the model that I had designed previously with task sets to replace it with options, but all the other details are fairly similar. So we have to do inference over an unknown size of space, but replacing task sets by options. And when he does that, the model captures really well participants' behavior at the first stage of a trial and at the second stage of a trial. Okay, so we can extend what we've been working on hierarchical reinforcement learning to much more interesting kind of complex behaviors like options. And we see that participants can mix and match for efficient learning, fast learning, and transfer of information. Okay, I'd like to thank my lab, in particular Jimmy and Maria, who are here and who have posters, and Sam, because the three of them are watching the baby right now, and advertise for open positions in my lab.